I am Parametric, and today I'm going to present on stroke mortality and morbidity in the United Kingdom. So this is a disclaimer slide, and today I'm going to go over some stroke definition, some important statistics, a brief description of the study, the patient numbers, I'll go over unadjusted Kaplan-Meier plots, how I checked my Cox proportional hazard assumptions, and how I used parametric regression fits and applied the double Cox model, and we'll see some results. All right. First of all, what is stroke? Stroke can be caused by a blood clot, this type of stroke is called a ischemic stroke. It is the most common one, occurring 85% of the cases. Stroke can also be caused by a rupture of blood vessel in the brain, and this is occurring in 15% cases. All right. The ischemic stroke and the hemorrhagic stroke are quite severe because they cause devastating effect. The brain cells starts dying as a result of starvation of important nutrients and oxygen. It causes permanent damage, which can lead to severe disability or even, sadly, death. Then we have the third type of stroke, which is called the transient ischemic attacks, or TIAs, or mostly known as mini-stroke, whereby the symptoms only appear very temporary and the damage is not so permanent. However, we should not take it so lightly because they serve as warning sign for future stroke. All right, why stroke is an important medical condition to study? It's because it's the fourth leading cause of death in the United Kingdom. And it's the biggest cause of major disability. As per a report of 2015, it was estimated that almost 2% of the UK population are stroke survivors, which makes up of around 1.2 million people. Almost 2/3 of stroke survivors will leave hospital with a major disability, and because of this, the NHS and the social care costs related to stroke are estimated to be 1.7 billion a year in England. And the economic burden, sometimes measured in terms of DALYs, that is disability adjusted life years, and this has been estimated to rise to 61 DALYs in 2020. All right, a brief description of my study. So I'm studying the impact of first ischemic stroke and first TIA, the impact on longevity and morbidity risk. My study spans from 1986 to 2017. I'm using a design of case control that is one case matched to at least 3 control, matched by age, sex, and GP practice. We are excluding cases, patients who have had major prior cancers, dementia, chronic kidney disease, like very severe ones, like stages 3 and above, and hemorrhagic stroke, because these are life-limiting conditions. Our primary outcome is the all-cause mortality, but we could also study other secondary outcomes like further strokes, dementia, such as the Alzheimer's and the vascular dementia, heart failure, myocardial infarction, and pulmonary arterial disease. Sorry. Right. Our model has been adjusted for all these type of covariates, such as different classes of drugs, different prior medical condition, as you can read on the slide, and some important demographic and lifestyle conditions, such as BMI, gender, age, smoking status, alcohol status. Right. I have 2 data sets, obviously, one for the ischemic stroke and one for the TIA data set. To understand what these boxes mean, let's go from the blue boxes. these blue boxes is like the big data set, like containing all the patients, the case, and the control. But this big data set has missing information, all right? I think Elias went over it and talked about a little bit of why data has missing information. And then from the blue box going to the yellow box, this is like the full case, like when we take out all of the record with missing variable, then we have all those record full information. So we have our full case data set. So we do survival analysis on the full case data set because that survival model will inform us for our multiple imputation data set. Now this is an adjusted Kaplan-Meier plot for the ischemic stroke patient and their controls. So we can observe quite a difference, and this difference is statistically significant and as shown by a log-rank test, which is very significant, as shown as the p-value being less than 0.01. So the black one is the control, and the green one are the cases. And as you would see, the median survival for the cases can be said to be 14 years, and the median survival for the control can be said to be around 23 years. If we have a look at the TIA cases and control, the same story, and but the median here for the TIA cases is estimated to be around 18 years here, and for the control is around 26 years. But this is unadjusted so far. Right. I started with a big model that is all my main factors and all two-way interactions, and I proceeded with a backward elimination to get a parsimonious model. Now, when I got this parsimonious model, I applied the Gramsch and Turner test to test the Cox proportional hazard assumption, and earlier Elias has gone through it and has explained how what the p-value means. The p-value is testing the significance of the correlation of the residual with time. So if you have a significant p-value, this just means that this particular covariate is having a time-dependent effect. So all those that have put in blue boxes are the ones who are showing that they might have some time-varying effects. All right, and as you would see, I've put in the red box, the global test statistics. This is very highly significant, like 2.8 to the power of minus 12. So it's definitely showing evidence of non-proportionality. Okay, so then I proceeded with a graphical diagnostic of this Gramsch and Turner test. Now, this one is showing no distinct pattern. Now, the next slide I'm showing you how the covariates that are violating the Cox proportional hazard assumption are behaving. So as you can see, there is a distinct pattern with time going on. So the first two are the one for two different birth cohorts, and the last one, I'm sorry, the lesion is not appearing there, it's for the group. So you see a general high hazard with time going on with cases, but all of these are just showing the same story, that it's a non-zero slope and it's clearly evidence against non-proportionality, against proportionality, sorry. Then to circumvent this problem of non-proportional proportional hazard assumption, we decided to take a parametric approach, all right? So first of all, I splitted my data into the cases and the control, and I applied different parametric survival distribution. And if you can see, the black one is the Kaplan-Meier one, and you would see the blue line is very close to it, fits it really nicely in the cases and as well in the control. And judging from the AIC, AIC stands for Akaike Information Criterion, which is just a statistical measure of relative efficiency of models. As lower it is, the better. So here we have the lowest is the Weibull in both cases. So why was chosen to model the baseline hazard? So this is the same slide as Elena, because I am using the double Cox model, but in the case where my my hazard is a variable, right? So it's the same double Cox regression explained by Elena, and this model has both shape and scale effect. So in my scale effect, I had these covariate, and for shape effect, I had both cohort and antiplatelet therapy. All right, before going through my results, I would just like to briefly talk about multiple imputation, but Ilias also has gone over it, but let me just say that we start with a big data set which has incomplete information, and we impute this information if we have a model of the missing variable depending on the existing variable. So we generate multiple sets of this completed data set, and we apply survival analysis on each of these data sets, and then we combine all these results using Rubin rules. Right. Now, here we have 4 different plots, so 4 groups. So the female controls, female cases, male controls, and male cases. So the different colors are showing the different birth cohorts effects. So this is clearly showing the shape effect of birth cohort and the shape effect of antiplatelet. Now, antiplatelets are what are drugs that are prescribed to people who already have unduly hypertension or established cardiovascular diseases, right? So we are observing here that, the dashed one are the people who are taking antiplatelets, and the solid lines are people who are not taking antiplatelet. And you would see the hazard is, for people taking it, is lower than people not taking it. So it's kind of protective effect of antiplatelet going on here. And also you can see the hazard is decreasing with time for later cohorts. And you can also see an effect of gender. Male has a little bit steeper, as you see the curves a little bit steeper, so a higher hazard, higher risk for males, right? So this is the forest plot given the other covariates. So based on the social deprivation, we can see the least deprived you are, the least the risk, the lower the risk, sorry. And obviously, prior medical condition confers higher risk. So as you will see, if you had prior CKD, you would have a hazard ratio of 1.33. If you had a prior heart failure, you would have a hazard ratio of 1.59. Now, the next one is a forest plot to show the effect of case control and age effect, and also the uptake of antihypertensive. The AHTN means antihypertensive. So if we go from top to bottom, we can see the age, as we go to different age categories, the risk is getting higher. If we compare the cases and the control, you will see each time the cases have higher risk than the controls. And if you observe people who take antihypertensive, they have higher risk. Now, why is that? Is because those who are taking antihypertensive are people who already have high blood pressure, so they are already medically impaired in a way. All right. That is all, and my future work is now to write 2 papers on TIA and for IS. I also have a model on TIA, but I could not put everything on this slide today, but we have 2 models, so I will write up 2 papers on the 2 different medical conditions and then translate it to an actuarial analysis. Thank you very much for your kind attention. Any questions?
Thank you, Padma. We have some time for questions now, please. Any questions? We also, yes.
So one of your charts, I'm not sure if you can go back, but it was that one there, yes.
Sorry.
That one, yeah. So in all of these charts, the later cohorts are lower than the older cohorts. So
Yeah.
is that really just because of other medical improvements?
Yes, that's showing kind of medical advancement.
So there is that sort of time effect
Yeah.
that's coming out of these plots.
Yeah. Any more questions?
But basically, this slide shows different shapes of baseline hazards for different predictors.
Are they all the same age?
Oh, they were of different age, and we actually, further you will see that we split age into several age categories. I mean, age at stroke was split into, but here this is baseline hazard, so it does not depend on the age. Age of stroke will add extra refinement to risks.
And in fact, is the zero in these charts, is that from the time of the stroke? Or
Yes, it is, yeah.
So it is,
that's why they start from the same place, yeah.
So, but if you've had somebody who, before the 1990, if they had a stroke 5 years earlier, so they're not in your data, or the stroke was out of the data, would they appear in your analysis, or is it, do you only include people who have a stroke where the stroke itself is within the observation period?
I think we only included people who had stroke within particular period, yes. Yeah. Other questions, please? Okay.
So the y-axis on that, is that cumulative hazard or just hazard?
Yeah, these are hazards, they're not cumulative hazards. But hazards should go up with time, evidently, because we all are aging. It's the shape of the hazards which is different.
I'm just confused why they're all starting at 0.
Or is that the Y rule? It's just a natural consequence of the Y rule distribution, perhaps.
Yeah, I suppose it is, yeah. Maybe we took out some bit, yeah.
Sorry, could you clarify on the definition of the case and controls, please?
The cases are people who have had a first TIA or a first ischemic stroke, and a control is a person of the same age, same gender GP practice, but who haven't experienced stroke or TIA.
I've got a question on the exclusions you mentioned in one of the slides. Are those exclusions based on the cause of death?
We are excluding patients who have life-limiting conditions because they would be people who would be dying really quick.
Okay.
But just come to the mic because you're very quiet. Just be closer to the mic.
All right. Did you hear me? Sorry. So I was saying we excluded these patients because these are life-limiting conditions, so these type of patients will die quite quickly, right?
Okay, but cause of death was based on only on stroke, or could be?
No, the cause, it's not, we are modeling all-cause mortality. We don't have the specific cause of death in our model.
Ah, right, okay,
Yeah.
okay. But shouldn't we exclude the cause of death, say, from accidents, which is not linked to
Unfortunately, we don't have this information.
We are excluding morbidity, not cause of death, because we want to look only at effect of stroke, kind of unimpeded, but other competing risks, because those people may die sooner because of those other conditions, such as cancer or whatnot. As far as the cause of death is concerned, I don't think the stroke, if you survive it, will be the cause of your death, unless you get the second stroke, of course. But you may die of cardiovascular disease, other cardiovascular disease, for instance, in the result of stroke. Okay. Other questions? Okay, then let's thank Padma once more for her talk.